Hello, today I will be presenting our work on COBRA, a framework for evaluating compositions of hardware branch predictors. The outline of my talk will be as follows. First, I will discuss some background on branch prediction, specifically on challenges involved with modeling and evaluating modern branch prediction pipelines. Then, I will discuss the COBRA framework and how the COBRA system enables a hardware-centric methodology for design space exploration and evaluation of complex predictor pipelines. I will also present our evaluation of COBRA-generated predictor pipelines, demonstrating how COBRA enables accurate and holistic evaluations of branch predictors. Let's start by examining the motivations for optimizing design space exploration of branch predictors. We observe two prominent trends which suggest that branch prediction will continue to be a critical performance feature in high-performance systems well into the future. First, the increasing heterogeneity and complexity of our software stacks suggests the continual importance of general-purpose performance. Second, we see development of commercial cores with wider and wider issue widths and out-of-order windows of many hundreds of instructions. Taking full advantage of these wide and deep pipelines relies on the existence of a highly accurate branch predictor. As a result, there is widespread interest in improving the accuracy of hardware branch predictors, with commercial systems dedicating more and more storage to the implementation of increasingly complex branch prediction algorithms and pipelines. I'd like to expand now on this observation on the complexity of modern branch predictor pipelines. We observe that modern predictor pipelines are composed of many interacting subcomponents rather than one monolithic design. Specifically, predictors with different latencies, learning different types of branches, interact with each other and with structures for maintaining branch predictor state. Just as an example, the AMD Zen 2 microarchitecture contains at least 7 different predictor subcomponents in its complete predictor pipeline. The complexity of these pipelines naturally presents a barrier to researchers interested in developing and evaluating their own realistic complex predictor pipelines. Finally, since branch predictors are typically tightly integrated into the microarchitecture of a high-performance core, we believe that the evaluation of branch predictors should be holistic as well, considering the issues that arise during the implementation and integration of a predictor within a high-performance core. Functional models of predictor behavior, while easy to understand and implement, do not capture real behaviors in high-performance systems, as they model the predictor sequentially fetching, predicting, and updating a single instruction at a time. Specifically, real predictors demonstrate behaviors like superscalar fetch, speculative prediction, pipelining, and out-of-order branch resolution when integrated into a real high-performance system. Additionally, we would like to be able to see the power, performance, and area trade-offs of branch predictors with respect to other core components. So for a holistic evaluation of a given branch predictor design, ideally, we should consider all of these factors. So keeping in mind what we've just discussed on the issues surrounding branch prediction, we believe that the ideal framework for branch predictor research should achieve the following goals. First, of course, we would like our approach to be able to describe predictors with state-of-the-art performance. After all, we are interested in advancing the state-of-the-art in branch predictor design. This implies a second point. Since state-of-the-art branch predictor pipelines are increasingly complex, our framework should support this complexity as well. Third, given that branch predictors are implemented in hardware, we would like to see a hardware-centric approach which is aware of the concerns and nuances with deploying hardware branch predictors. Finally, we would like this framework to be productive. We would like it to support rapid design space exploration and evaluation of diverse predictor designs. Given these criteria, we took a look at existing approaches for branch predictor research. Much research on predictor design is performed on software simulators, either functional or cycle-accurate. Examples include simulators like ChampSim, CVPSim, Gem5, and SimpleScalar. While these simulators provide very productive frameworks for design space exploration, as designers can leverage existing software abstractions and high-level programming languages, these simulators fail to provide both a holistic and productive design system, in the sense that cycle-accurate simulators can only simulate designs very slowly, and functional simulators do not capture the fine-grained details of a predictor executing within a high-performance system. In comparison, the development of many open source cores provides a new opportunity for designers to evaluate a predictor holistically within the context of a complete core that is already available to them. We took a look at the branch predictor pipelines in several open source cores, including the Pulp cores, Rocket, Boom, and Risky OO. And we found that these interfaces generally do not provide, or they do not support the complex predictor pipelines we would like to study, and they do not provide productive abstractions for designers implementing such complex pipelines. This makes it very difficult to develop a high-performance predictor as part of one of these cores without additional abstractions. So given our observations, we developed COBRA as a framework which preserves the productivity and capability of software-based modeling approaches while providing the holistic evaluation of predictor designs that only a hardware-centric approach could provide. The COBRA framework can be outlined as followed from a very high level. COBRA provides a unified abstract interface for the implementation of a predictor subcomponent. A library of subcomponents can be generated and composed via the COBRA topological predictor representation to generate a complete predictor pipeline. The final predictor pipeline can be synthesized and implemented within a real high-performance core to support holistic evaluation of generated predictors. I will now start by discussing the COBRA predictor interface. The COBRA interface is abstract and comprehensive, supporting superscalar and hierarchical predictor subcomponents, as well as supporting prediction of branch target and/or branch direction. On the right, you can see two examples of simple predictor subcomponents that might be implemented in this interface. First, a simple branch history table which can learn the predictions for a vector of branches, demonstrating support for superscalar prediction. Second, we show a tournament selector which can learn to select between multiple predictions provided by other subcomponents. This is a recurring idea across many predictor subcomponent designs, which learn to select or override some base prediction. The abstract predictor interface also provides unified signals for predict and update, making it easy to write correct, functional, and performant RTL for a given predictor subcomponent design. To demonstrate the generality and flexibility of the predictor interface, we implemented a diverse set of base predictor components in Chisel RTL and provide them as part of COBRA. These subcomponents are all parameterized to enable design space exploration and contain enough diverse features to implement a broad set of predictor pipelines, as we will see later. Note that in addition to basic counter tables and multi-level BTBs, we also implemented more complex algorithms like Tage and a loop corrector, demonstrating the flexibility of our interface. I also want to draw your attention to the predictor software model. While the other 5 sets of predictor subcomponents were all implemented as synthesizable RTL, the software model of a branch predictor component is an interface to a C++ implementation. This is provided to enable evaluation of a high-level algorithm written in C++ in the context of a complete core. This enables prototyping of advanced predictor algorithms without RTL implementation and holistic evaluation of such algorithms in the context of the complete core as well. So given that we have a library of hardware predictor subcomponents all in RTL, all implemented to some common interface, the next task is to compose those subcomponents into a complete pipeline. This is a challenging task because predictor subcomponents might have varying latencies, they might predict for different types of branches, and some may override the predictions of other subcomponents. The observation that the arrangement of a given set of subcomponents into a complete pipeline is a fairly complex task. This observation informs the development of COBRA's topological model for a predictor pipeline. To demonstrate how this topological model works, let's consider this simple predictor design, in which a tournament selector selects between predictions provided by a locally indexed pattern table and a global history indexed pattern table, and is finally augmented by a loop predictor which learns to exit regular loops. In this model, the abstract topology is simple. The loop predictor provides the final prediction in the event the predictor hits, otherwise the output of the tournament selector is used. From this abstract topology, we can easily generate the RTL description for the complete pipeline in the COBRA system, simply by specifying the edges of the predictor subcomponents. On the right, you can see the high-level description of the topology and also the code which represents this topology in the COBRA generator. The real power of this topological model is evident when we consider an alternate arrangement of these base predictor components. For example, we might want to consider having the loop predictor learn to augment the globally indexed pattern table instead of the final result from the tournament selector. In a monolithically implemented predictor pipeline, implementing such a change might be tedious to implement and debug. In contrast, the COBRA topological representation makes generating this modified pipeline very easy. To represent this design, we simply reorder the edges between the subcomponents. This is a one-line change in the COBRA generator interface. This flexibility makes it very easy to explore and evaluate a wide set of possible predictor topologies. The COBRA predictor composer interprets the topology to generate not only a synthesizable predictor pipeline from the predictor subcomponent library, but also the surrounding infrastructure for maintaining the predictor. This includes things like the global history register, the local history table, and the predictor update and repair mechanisms. The size, capacity, and behavior of all of these structures are parameterized based on the desired predictor pipeline, and they are all generated alongside the predictor. This makes it very easy to integrate a COBRA-generated predictor into the instruction fetch unit of a high-performance core. In this diagram, we see how the generated components, in green, provide a prediction on every cycle to the front-end control and redirect logic, and also receives branch updates from the back-end of the core. This narrowed and precisely defined interface makes it easy to integrate COBRA-generated predictors into real cores. To demonstrate the usefulness of COBRA for holistic branch predictor evaluation, we integrated the COBRA predictors into the front end of BOOM, an open source RISC-V out-of-order core. BOOM was configured to be representative of a modern high-performance machine with 8 wide issue and 16 bytes per cycle fetch. 3 diverse predictor topologies were described and implemented out of the COBRA predictor subcomponents, including a high-performance Tage-like design, which is meant to be somewhat approximate to the current state-of-the-art in branch predictor algorithms. All predictor designs were implemented using the COBRA framework and generator, and they were all composed out of a library of individual predictor subcomponents, which I have described previously. A detailed description of each of these designs is provided in the paper. First, we wanted to confirm that the COBRA-generated predictors were physically realizable and realistic. We synthesized the predictors together with the 8-wide BOOM core in a commercial 22-nanometer process and found that all the predictors were able to synthesize at 1 gigahertz. Remaining critical paths were elsewhere in the core. We additionally evaluated the area cost of each design and found that the COBRA-generated RTL, the area of these predictors, was reasonable for their size and designs. These results confirm that COBRA enables physical design-aware evaluation of branch predictor designs, as we can compare the relative performance of these predictors with their expected area costs, and also compare the cost of these predictors to the costs of other core components. For performance evaluation, we wanted to check that COBRA-generated hardware predictors can achieve state-of-the-art prediction accuracy compared to existing open source and commercial cores. For these experiments, we used the FireSim system to run FPGA simulations of the COBRA augmented BOOM cores with the 3 previously described predictor designs, running the full Spec 17 and Spec 06 workloads with test inputs. By leveraging FPGA accelerated simulation of a complete core, we can evaluate predictors on a complete workload over trillions of cycles, matching the performance of a trace-based software simulation while providing much more detailed simulation fidelity. The results from these evaluations indicate that the COBRA-generated predictors not only exceed the performance of existing open source predictor implementations, they are also comparable to the commercial Intel Skylake and AWS Graviton cores. On Spec 06, the best COBRA predictors achieve over 2 times fewer mispredicts compared to the original BOOM predictor, and over 3 times fewer mispredicts than risky OOO. On Spec 17, we find that the best COBRA-generated Tage predictor can achieve comparable number of mispredicts to the Intel Skylake and AWS Graviton systems. This demonstrates how COBRA can support holistic design space exploration of state-of-the-art branch predictor systems. We also explore 3 case studies of areas where a holistic COBRA-based hardware-centric approach can reveal new insights into branch predictor design and integration that are difficult to show through purely software modeling. The first case study discusses the effect of predictor latency on overall IPC. The second discusses the nuances with speculative update and repair of branch predictors, as branch predictors are typically updated and managed speculatively in a high-performance core. The third case study discusses the relationship between core backend optimizations and predictor performance. For more information on these case studies, please see the COBRA paper. In conclusion, the COBRA framework enables holistic, hardware-centric evaluations of branch predictor designs. By providing an abstract predictor interface and predictor composer, COBRA enables the designer to productively write RTL implementations of branch predictor subcomponents and integrate them into physically realizable and realistic predictor pipelines that can be holistically integrated and evaluated within a real high-performance core. We also demonstrate how COBRA advances the state-of-the-art in open-source hardware branch predictors, as the TAGE-like COBRA-generated predictor pipeline achieves superior accuracy compared to any open-source core and comparable accuracy compared to state-of-the-art commercial designs. COBRA has been open source. We provide the source code in 2 repositories. The first one, just COBRA by itself, and the second one demonstrating how COBRA was integrated into the BOOM core. Before I finish, I'd like to thank my collaborators and my advisor for their help and advice, without which this work would not be possible. Thank you for watching my talk.